my talk will be around the morphology of this fracture, and we will try to cover scale from small hand sample, and we will go to almost the micron scale, to the scale of fold surfaces, so meter to several meters, to even the scale of the shape of continents, because continents is plates that break, and some of the shape of Africa, for example, is this part. It looks very like the South America. It's just because these two parts break away, so it's like a big fracture. And can we say something about the shape of this kind of continent compared to the shape of the fracture? So we started that like 3 or 4 years ago because in Grenoble seismologists were interested by that, because they were asking, for example, when you have a rough surface like that and you have an earthquake, would you have something, a seismic slip, or would you have just a creep? What is the stress drop? So a bit like what Anders has presented, if you start to have a rough interface and you start to slide these springs, what would happen because the interface is rough? How does it control the stress distribution? So that's all the questions they asked me, and finally I decided to study them because I just found it was nice, and that was sufficient enough to study them. So what do they look like on the field? So for example, that's a typical fault zone in, this one is in Nevada. So there is somebody for scale here, and there are some slip surfaces. So here it's a whole mountain, and the basin at the top has moved 1 kilometer down, and you have some slip surface like that. And this slip surface, they look like that with striations, and these striations indicate the sense of motion during slip along this interface. With some recent tools that are called LIDAR, laser distance meter, it's possible now to measure this surface, the topography of this surface, at a resolution of millimeter to several millimeter, and you can get some kind of 2D map of the surface, and from this map you can extract profile. So here, profile perpendicular to the direction of slip, and you see this kind of corrugation, and in the direction of slip you'll see also you have tiny variation, and this tiny variation is not the noise of the apparatus, it's really tiny variation in the roughness of the slip surface. So I will talk during my presentation about this kind of signal and this kind of surface, and we will try to find a way to characterize this, the morphology of this surface. So one way to do it is to look at the scaling properties of this rough signal. So that's two rough profile, and the idea is to look at the portion of length delta x and height delta z, and try to zoom in and see how you should zoom in the z direction to get a statistical similarity as the previous scale. And when you do this kind of zooming, there is a small exponent here, which can come out. It's not automatic, you have to look for it, but sometimes you find it. And that's what I will talk about today, is what is the value of this exponent in all the fault or all the fracture you can find on the Earth. So this idea of having this kind of scaling relationship, it's there is a paper in 67 by Benoit Mandelbrot, who came in Oslo quite often, and it comes from this guy Richardson, who was a geographer. And Richardson, he was a bit frustrated because he was looking at atlas of different places in the world. And for example, in this atlas, you compare two atlas and you look at the length of coastline of a country, and in one atlas it's very small, and in the next atlas, the length of the coastline of the same country is different and could be larger. And he tried to understand that. And it came with this idea that if you look at Great Britain and you measure the length of the coastline, if you use a ruler of one size, for example 200 kilometers, the length of the coastline of England is 2,400, and if you use a ruler with a smaller size, the length of the coast of England is larger. And you can find a relationship between this length measured and the size of the ruler, and there is this exponent here which comes in, and when you do a log-log plot of this kind of relationship, so that's a log of the length, log of the ruler, and that's where the coast of Britain stands. If you do that for a cycle, for example, you get something which is flat. And that's the concept of what is called the self-similarity of a curve. The fact that if you measure this curve at different scale, you will get different lengths. in nature, what we will find is, so I tell you the result now of what we will find, and that's an important transparency. What we find is that when you have fracture surfaces, if you do this kind of analysis, you get some scaling exponent, which is called the Hurst exponent. And this scaling exponent is less than 1, is smaller than 1. It means that if you increase the scale of the surface, because this value is less than 1, so it's something to an exponent smaller than 1, the surface will look more and more smooth as long as you go upper in the scale. So that's, for example, a fault in nature, let's say 20 kilometer by 60 kilometer. It looks like rather smooth, but if you start to zoom in 5 meter by 5 meter, you see this fault start to be very rough. And an important issue with this kind of description in fault in Earth is that if you start to propagate an earthquake on this surface, at a small scale, the earthquake will see very rough surface, and at the large scale, the earthquake will see a quite smooth interface. So how do we measure this exponent? So one way to do it, there are many methods, but we will use one, is just to take this signal and to take its Fourier transform, to take the modulus of the Fourier transform. So that's here the wave number, so it's 1 over a wavelength, so here it's 1 over a distance, the Fourier module. And when you get some kind of, in the log-log plot, a line here, a straight line over a couple of decades or several decades, this straight line is related to this exponent h. So let's go now to the data. So I will show you 3 kinds of data. One of them is fault on the outcrop, fault on which some earthquake occurred. Another set of data is earthquake traces. So when an earthquake breaks the earth, you can have this trace of the earthquake, and that's a rupture. And the last one will be this continents I showed you before. So we went on the field and we tried to find this kind of surface. So this one comes from an outcrop in Turkey, on which an earthquake occurred in 1942. It was magnitude 7. So this earthquake broke the rock, and you see some striation. So on this outcrop, there were 2 meters of displacement during this earthquake. And what we did, we scanned this rupture surface at different scale. So at the scale of meter, to the scale of centimeter, and even to the micron scale. So we could have some piece of this surface at a resolution from 1 micrometer to 1 centimeter up to surfaces that are meter long. And we analyzed 5 surfaces like that. So that's another one. This one is in the middle of San Francisco. Same kind of rupture surface with the striation indicating the direction of slip. And this surface was scanned at different resolution. And for all these fault surfaces, when you do this Fourier transform analysis, what you get is this kind of thing. Is that, so the different curves correspond to different scale analyzed from 0.1 millimeter to 10 meter. You get this kind of scaling relationship. Sometimes here when the spectra flatten, it means that you reach the resolution of your apparatus. But all the way you get some slope with an exponent here which is close to 8.8. And that works for all the faults we analyzed. Let's go now to bigger scale. So we switch now to the meter to tens of meter scale to 100 meter to 100 kilometer scale. And let's go on the real faults or real big faults. And for example, the North Anatolian fault is this big fault that separates the Arabian plate and the Anatolian plate from the Europe. And along this fault, perhaps 60 kilometers of displacement was accommodated by the rotation of this plate along this interface. And this fault is also famous because in 1999, 2 segments broke. So this segment broke in July, and this one in August, giving to a magnitude 7 earthquake. So on the field, this fault, you see that because when you have an earthquake, it's displacing some markers. So for example, you have rails. You have this line of trees that have been displaced. Here it's the trace of the fault, and this building was just below the fault and didn't survive. And the idea is just to map this trace over kilometers and kilometers and get some trace of the rupture of this earthquake. And so the data I have used, it's this kind of data where in red, that's the fault trace map before the earthquake. And in blue, that's the earthquake of 1999. You don't have data here because it's two lakes. So there is a small lake here, another one there. So you don't have data of the surface rupture in the bottom of the lake. But the rupture here started there and just moved in this direction. And these traces, they are a bit rough. It's not completely flat, so they have their own roughness. So we use the Turkey data. We use also some tens of surface rupture data. This one is an earthquake in California in 1992. So the earthquake broke 3 fault segments, 1, 2, 3, over a distance of 65 kilometers. And the roughness amplitude of this surface trace is something like 5 kilometers. So if we put all these data on the graph and do the Fourier transform for all this earthquake, we get also all this kind of power law over 2 or 3 decades with an Earth exponent or an exponent which was similar to the fault in the field. And let's move now to even bigger rupture. So I have selected 3 of them. A very recent one, which is the opening of the Red Sea. So the Red Sea is opening since the past 5 million years. This side of Africa opened around 170 million years, and this side of Africa around 100 million years. So it's just a continent that starts to break. And the idea that this coastline, so the data here is coastline, and this coastline should be a marker of this big rupture that broke this continent at that time. When you use coastline, you have to be a bit careful because you have, since this fracture form, this big fracture form, you can have some secondary effect, like when there is a river, it creates this kind of estuaries that will modify the coastline. You can have the fact that when you have cliff, you have erosion, so the continent will be eroded from one side. Well, all these things, let's say that they have length scale below 50 kilometers, and I will just consider length scale above 50 kilometers for this big, for this continent. And the result of that is doing the Fourier transform, so that's the data. That's the west side of Africa, the east side, that's the 2 Red Sea. So, below 50 kilometer length scale, we have some noise, some defect, but above 50 kilometer, again, an exponent which is quite well defined. So the result now, if we put all this data together, so that's the Turkey data, the earthquake, the continent, and if you add on that the fault on the surface, you get this kind of trend, which go from 0.1 millimeter to one couple of thousand kilometers. Individually, all these trends have an exponent of 0.8, and then if you just average all these trends, you get also 0.8. So here is the size of 100 micrometer. That's the biggest fault, at least I could find on Earth. So that's one of the results, but now we could ask why is it like that, and that's where the problem comes. And from this kind of data, I would like to ask 2 questions. Is that why this? And if you take a given length scale, you see that there is a bit of scatter, vertical scatter. And how can that be explained? I don't have an answer for these 2 questions, but I have some ideas how to tackle them. So one way to tackle these 2 questions, so first, this 0.8, it has been found in rocks, in glass, metal, ceramics. The idea is that when the crack propagates, the rupture propagates, in front of the rupture, there are some defects. So that's a rupture line that propagates. In front of the rupture, there are some defects. This line will see this defect and start to be perturbed by this defect and gain some roughness. And a nice way to describe that is to use this kind of equation which describes the roughness of the line as a function of some elastic parameter of a noise term. So that's the term which takes into account the presence of defect in the medium. And this term which says that, so that's a difference of height between 2 points here, 2 points in the line, divided by their distance to the square. The idea is that if a point of a line here see a defect there, it will interact elastically with another point of the line. So a point of the line here will interact with a point on the line there through elasticity, and that's where comes this exponent. It just means that this interaction is decreasing with 1 over the distance to the square. The problem is that if you use this kind of model, you get an exponent which is close to 0.4. So we are far from 0.8, but if you start to change this interaction, saying, for example, that 2 points, they will interact, but in a bit weaker manner than elasticity, you can end up finding something close to the 0.8. And there are some experiments and simulations which see this kind of effect of damage, presence of damage. So that's a kind of experiment where you have a notch, 2 pieces of, I think this one was a metal, and a crack propagating. And this crack propagated by, so it becomes rough, because it started to create, either to create its own damage, some cavitation in front of the crack tip, or just meeting some heterogeneities. And there are some simulations that reproduce this kind of effect where the crack front starts to wander and becomes rough. And you can even do that at the atomic scale, whereas in kind of molecular dynamics simulation, the crack grows. There are some cavity that form ahead of the crack, and then it creates some kind of roughness. In nature, there is another explanation. And that comes from at least some field observation and from some experiments of taking a piece of rock, so a slab, the size here is 6 millimeter. It was just squeezed in a biaxial manner, so loading was from the top. The 2 sides here were loaded also, but with a smaller load. And then this kind of fracture started to form, so that's some faults that start to deform, and you have these 2 families, 2 conjugated families of fault. And by doing this experiment and putting a camera in front of the experiment and looking how this fault develop, you can follow the same fault at 2 different stages. So that's this one is this one after 1 increment or some increment of growth. And what you see that, for example, this fault developed by, you have many small fractures. These small fractures start to interact, so they interact and will merge, but they will merge creating this small lens that will become trapped. And at the end, the fault surface is rough, it's not flat, and it's due to this all these small local interaction which create this small topography. And it's summarized in this kind of drawing where many cracks start to grow together and interact. They will interact by creating this lens. And in this experiment, the scaling between this height and this length, so it's some kind of scaling of the roughness, can be measured with an exponent here, which is 0.6, 0.7. So we are not close to 0.8, but we are not very far yet. The other question we try to ask also is that why do you have so much scatter here? So why all these curves are not on the same line, but there is a bit of vertical displacement? And an explanation could be that at least there is this experiment that was done a couple of years ago of using a material in which the disorder was controlled. So the size of the disorder into the material could be varied, and this roughness scaling could be characterized and was depending. So the vertical position of this line was depending on the initial disorder in the system. So the size of the disorder or the kind of disorder in the system should control this amplitude of the topography. So just to conclude, I think that this kind of observation, which go from 0.1 millimeter to 1,000 kilometer, the overall trend and each individual surface or fracture we analyze show this kind of scaling relationship. Why is it like that? I'm not sure we know yet, but that's surely the time to try to understand it. Thank you.